Modern neuroscientific techniques to study the language in the brain have utilized fewer patients with brain damage and more individuals who have normal functioning brains. The first attempts at doing this were quite primitive and involved a balancing table. Angelo Masso would place people on a table that was balanced on a pivot and ask participants to engage in some mental task. Once the mental task began, he would try to observe whether the individuals would come off balance, whether their head would sink lower than their toes on the table. If so, that would suggest to Masso that the blood had flowed to the brain. Masso observed that more cognitively demanding tasks would sink the head part of the body lower than other less demanding tasks. Our modern techniques are a bit more sophisticated than that, but they rely on the same principles. For instance, functional magnetic resonance imaging, or fMRI, is the most common type of brain imaging technique that's used today, and it's really quite revolutionized the study of the brain. But fMRI isn't actually studying which areas of the brain are active, like which neurons are active. It's studying differences in the oxygenation of blood. The technology works by lining up all the protons in a person's body inside a magnet bore. And once they're all aligned together, it uses radio frequency pulses to knock them out of alignment. Now, hydrogen protons will come back into alignment with the bore of the magnet, or that center where the person's body is, at different rates depending on the kind of tissue that hydrogen proton is in. And so, if there's some area of the brain that has blood that's deoxygenated, the hydrogen protons are going to align at a different rate than in areas of the brain that are more oxygenated. In other words, the technology is going to attempt to observe which areas of the brain have more oxygenated blood, suggesting that those areas have been active and have required the blood to bring more oxygen there to feed the neurons. So it's an indirect way of measuring brain activity, but we still think it's a pretty reliable one. The problem is, we've learned over time that most of the brain is active all the time. You may have seen a movie or heard some myth before about the fact that we only use about 10% of our brain. That's simply not true. We use almost 100% of our brain all the time. And the difficulty with that is, if we stick somebody in a scanner and we measure which areas of their brain have oxygenated blood, we're going to find that most of the brain has oxygenated blood all the time because all of it's being used. So in order to get at which tasks require specific linguistic components, we have to put people in a scanner and compare their brain in two conditions, subtracting the brain oxygen levels in the one condition with the other condition. So in order to get the best comparison, we want to make sure that these two conditions look approximately equivalent, but that one condition does involve some linguistic processing, and the other one is almost exactly the same, but doesn't require some linguistic processing. So one example described in your text on page 79 and 80 is to put people in a scanner and have them listen to linguistic input or musical input. And by comparing the brain oxygen levels in those two conditions, we can subtract out all those brain areas that are active all the time and just ignore them. But what we'll find is, if we take like an area of the brain that requires more oxygen during some linguistic processing, and we compare it to that same area of the brain while somebody is not engaging in linguistic processing, then we'll see that during the linguistic processing they will have used more oxygen in that area, and so it will show up as a peak activation. They'll be active in both situations, no matter what the individual is doing, but it will be more active during the one task than in the other, and that will show up in the fMRI scan. The caution that ch3 provides us with at this point is the reminder that just because we've taken one task and we theoretically think that it requires some linguistic processing, and we take another task, like music, which we think doesn't require linguistic processing, that doesn't mean that we're right. Like, let's say, for instance, that we make this comparison, and we come to the conclusion that a certain brain area is activated in linguistic processing but not used in music processing, and therefore we have identified the area of the brain that's involved in language, and we've we've pulled out all of the regions in this analysis that are required for just blanket auditory processing that doesn't have linguistic components. It's possible that rather than our explanation being correct, that a better explanation might be that the same areas of the brain that allow us to do linguistic processing are also required in order to process musical kinds of input, and that really if we were to use a different kind of auditory task that wasn't musical, but that was just like listening to white noise or listening to various sounds of a kid running sticks along a fence or listening to an elephant cry, then we might see that the areas of the brain that are required for musical processing are actually the same ones that are required for linguistic processing. Now, I'm not saying that that's the case, but I am reminding us that we need to be cautious about the kinds of comparisons we use when we're making methodological decisions for a study of language processing.